Hello, welcome everyone. Today we have the second part of this course on Lie systems and compatible geometric structures by Professor Javier de Lucas from the University of Warsaw. So Javi, whenever you want.
Oh, thank you, Xavi. Well, I will continue from the end of the last talk, and I will repeat a couple of things I did the last time quite fast. So let me recall you that this talk is about a class of differential equation, ordinary differential equations called Lie systems. At these Lie systems, they are differential equations for which the general solution can be written as a 13th function of affinity family of particular solution of one constant. I mean, you have a differential equation, okay, and you are able to describe the general solution in terms of affinity family of particular solution of a certain constant. This is, for example, what happens when you have a linear system of differential equations. First of all, the differential equations with time-dependent coefficients, yeah? But it's more general because for this system, you learn, some of you at the beginning of your degree, the superposition is linear, okay? But a superposition rule in general can be a nonlinear function. This is a nonlinear function. So I told you the last time that these systems were studied for the first time toward the end of the 19th century by the famous Sophus Lie, the one who developed the Lie group theory, Lie algebra theory, and many other topics related to these structures, and other researchers also were involved. And I told you that for a long, long time, the topic was almost forgotten till the 80s, 70s, 80s of the 20th century, when start studying the system, these Lie systems again. Indeed, he did it here where I'm working now in the Institute of Research Mathematics of the University of Montreal. And then Winternitz worked on this topic by himself and with many, many other researchers. And this, well, Winternitz has something, I don't know, more than 400 papers. And on this topic, he spent something like 10 years working on it and doing a lot of jobs, articles on Lie systems. So listen to the proof, a lot of people from this institute, from the Centre de Recherches Mathématiques of the University of Montreal, and after these works, they were working on it, okay? But from another point of view, Winternitz was studying Lie systems to look for applications mainly. He also studied the stochastic differential equation, numerical systems, things of the sort, Lie algebra, vector field related to Lie systems. But most of these work were, well, let us say that they were not too much mathematical, let us say it this way, okay? He had lots of ideas, he found lots of applications with not only ordinary but partial differential equations, but they were not the sort of works made by mathematicians. Instead, toward the end of the 20th century, from the University of Zaragoza in Spain, Marmo from the Institute of Nuclear Studies in Italy, in Naples, and Grabowski from the Institute of Mathematics of the Polish Academy of Science, they started studying Lie systems by means of geometric techniques, in a more geometric way. And they developed an approach to the Lie systems that were based on foliations, on bundles, and things of the sort. So I call this the foliation approach. The other way to study Lie systems is the Lie group approach. This is another one. It was developed by this Poisson toward the end of the 19th century and the beginnings of the 20th. So let us say that Winternitz did everything, and then to study the system, there is a approach based on foliations, on connections, a very geometric one based on these structures of bundles, And there is another approach that is based on the use of Lie group actions and Lie groups. So these are the main approaches to study Lie systems. So the first part, well, let me recall something I did the last time quite quickly. And let us review the Bézier approach to Lie system, that it is based on the use of Lie groups and differential equations on Lie groups. So the main point of this approach was noticed by Bézier. It is that every Lie system on any manifold can be solved by means of a Lie system on a Lie group. Indeed, a Lie system of a particular type on a Lie group. So Lie systems on Lie groups, they are one of the most important classes of Lie systems. Okay? It's not written specifically in here, but I will explain it in a while, that the way of relating a Lie system on a manifold and the associated Lie system on a Lie group is by means of a Lie group action. The only problem in this approach is that this Lie group action can be quite difficult to get. If this is the case, this approach is rather unuseful. Okay, but in many cases you can do it and it can be applied, and then it has lots of applications, numerical systems, and well, there are lots of things. So let me explain how this looks. Let us take a Lie system on a manifold N, and let us consider as before that this Lie system has a Bézier-Goulbel Lie algebra B. I recall you that the Bézier-Goulbel Lie algebra is nothing but a finite-dimensional Lie algebra of vector fields on N. And I recall you that the Lie theorem tells that a Lie system, or a system of first-order differential equations, non-autonomous system of differential equations, is a Lie system. It has a superposition rule if its differential equation can be related to a time-dependent vector field taking this thing in this finite-dimensional Lie algebra B. So let me recall you something about differential geometry that maybe you know, maybe you don't. The thing is, when you have a certain finite-dimensional Lie algebra vector fields, okay, there is always a Lie group action acting on N in such a manner that the fundamental vector fields of this Lie group action are exactly the vector fields of the Lie algebra B. Obtaining this Lie group action is what is called the integration of the Bézier-Goulbel Lie algebra. Okay, so let me recall you that the fundamental vector Lie group action is just the set of vector fields generated by the action of the uniparametric groups of G acting on the manifold, and this is more or less what it is. So this is in here. What is written afterwards is the definition of this fundamental vector field. So look this way. Okay, you have your Lie group, and you have the tangent space to this Lie group, yeah, and you have a basis of this tangent space to the neutral element of the Lie group. So the fundamental vector fields are the vector fields given by this expression. At a point x, the vector field x alpha is the differential in terms of time for time the t of the action of one curve in the group, the exponential minus t a alpha. This is a one parametric subgroup of the group acting on x. So you see that by construction, these fundamental vector fields are tangent to the orbits of the Lie group action, because when you pick up a point x, what you are doing by doing the action of the exponential is to take the action of the uniparametric group subgroup of G on x. And so you are taking one direction inside the orbit of the group G passing through x. And by this definition, x alpha will be a certain vector field tangent to this orbit. When you pick all the fundamental vector fields, all these fundamental vector fields are spanning the tangent space to the orbits of the group. So these vector fields are very important because they are telling you which is the distribution tangent to the orbits of the Lie group acting on N, on the manifold N. So when X is a Lie system with a Bézier-Goulbert Lie algebra B, please recall that by the Lie theorem, the time-dependent vector field can be written as a linear combination with time-dependent functions of a certain family of vector fields X alpha. For certain time-dependent function B1t, BRT, that's not bad. The thing is that they exist. So let us continue. And now, when you have the Lie group action, okay, that can be constructed, there is a theorem that tells you that when you have the Lie algebra vector fields, please note that this thing in here are integral cubes of X alpha, because you know, when you pick up this cube, the tangent space, the tangent to this cube is the value of the vector alpha. So here, these expressions, they are integral cubes of this thing. So note that this tells you how this must look like. When you have this X alpha vector field, what you have to write in here are the integral cubes of X alpha, which are essentially unique. So by knowing the integral cubes of this, you will know the action of these elements of the group. Okay, and by knowing this thing for every element of the algebra, you can construct the Lie group action. Now, when you have a Lie group action with a group G acting on N, there exist 30 mappings that they are associated to each, and they are associated for every Lie group action. One is the restriction of the Lie group action to a point of the manifold. This is the phi X map. So this map is defined the same. Then when you have an element of the Lie group, the image of this phi X on J is nothing but the action of G on the point X. So you see, what is doing this is picking one element of the group, and you obtain the image of the action of this element at X. So when you have this mapping, the image of this mapping is nothing but the orbit of the action of the Lie group G at the point X. Now, once you have this map, you can write the fundamental vector field of the Lie group action by means of this map. So remember that by definition, the fundamental vector field X alpha at the point X is the time derivative of this expression. Yeah, this is the definition. But you have to take into account that this curve is nothing that phi X acting on this curve, but this curve is the integral, is a integral curve, okay? It's a curve whose tangent vector at t equal to series a minus a alpha. So by definition of the tangent map to phi X, this thing is exactly this, okay? Because you see, the definition of the tangent mapping to phi X at the point E, the neutral element of the group, with an element of the Lie algebra alpha, or minus alpha, you put it inside, is nothing but the derivative of phi X acting on the on a curve whose tangent vectors I alpha. I mean this. So once you have written the fundamental vector field X alpha in this way, you can see that this expression for the time-dependent vector field can be written in the following manner. You have this X alpha of X, you put this in here, and taking into account that the tangent to phi X at the neutral element is linear, and these are just functions depending on time, you can put it inside this mapping, and it turns out that the time-dependent vector field at point X is defined for every X by means of a curve in the Lie algebra, okay? And this curve is exactly the same no matter the point X is. So all the time-dependent vector field at every point x and every time t can be written in this way by means of a curve which just depends on t. So this curve is very important, and it can be used to define a certainly system on Lie group G. How this looks like? Okay, these things, you say this A alpha, they are elements of the Lie algebra of the group G. That means that it's the tangent space at T of the Lie group with certain coefficients, yeah? So let us define the following thing. These system of differential equations on the Lie group. This, you have that for every t, this is an element of the Lie algebra. So you can work out the right translation, the tangent to the right translation, and what you obtain here, it will be the following thing. Recall that on a Lie group, the right invariant vector field at a point G, alpha, is defined to be the action of the right translation, tangent right translation at the point E, the neutral element, of the value of the right invariant vector field at the neutral element, which is by definition A alpha. So if you use this, you will see that this differential equation can be written as follows. Pick up this. A alpha, as it is the sum for alpha equal to 1 to n of this linear combination with a minus. And then, since this is a mapping on the Lie group, and the time here is just a coefficient, you can put out the coefficient out, remembering that this map is linear, and by applying the tangent space, the tangent mapping to RG at the point E to A alpha, by definition, the right invariant vector fields, we get that this is the value of the right invariant vector field alpha x alpha at the point G. So you see, this differential equation can be understood, okay? The tangent to at any time t for solution is given by a time-dependent vector sum, a linear combination with time-dependent functions of a set of vector fields spanning a finite-dimensional Lie algebra, because these are right invariant vector fields. And you know from differential geometry, from Lie group theory, that right invariant vector fields span a finite-dimensional Lie algebra. So this is indeed a Lie system. And this part is just defined to be a time-dependent, because it depends on time, right invariant, because each of these parts is right invariant, vector field. And our system is a Lie system. So what tells you here is that we have related a Lie system with a third-time Lie system on a Lie group. Groups of this type are called automorphic Lie systems. Okay, and they are always Lie systems on Lie groups defined by right invariant vector fields and arbitrary time-dependent coefficients. So we have related so far a Lie system on a 13 manifold with a Lie system on a Lie group of a particular type. And it's important to remember, take into account, that all the properties of the Lie group, if it is solvable, if it is not solvable, which are the quadjoint orbits, or if it admits invariant metrics or some invariant, B invariant volume for whatever, they can be used to study this system. And in turn, this automorphic Lie system can be used in a Lie system. Now, the following proposition tells you that when you have a 30 Lie system and you define the associated automorphic Lie system, the general solution of the Lie system can be worked out, can be obtained by means of just one particular solution of the automorphic Lie system. This is very important because for standard differential equations, most differential equations, you are not able to know the general solution. It's very, very difficult to get. I know that for students, you think that, well, you can have the feeling that all differential equations can be analytically solvable and you know solutions. Rather, it's a fake impression. I mean, most differential equations can not analytically solve. You need numerical methods. And, well, you have to know how to deal with that. Normally, it means that you need artificial intelligence, or you need numerical methods, or you need an approximations, or you need certain approximations. Yeah, you need many things. The thing is, when you have a certain differential equation, and for example, you want to apply a numerical method, and the general solution can be obtained by means of finite family of particular solutions. This is a very, very useful stuff, because it means that if you have one algorithm and you apply it to solve 7 cases, say with particular solution, you will obtain essentially everything. And normally you cannot do that. And this theory is even stronger, because it tells you that when you have a certain Lie system, if you go to the Lie group, you just need one particular solution to obtain the initial Lie system. And you say, how it comes that you can do so? Well, the main thing is that somehow this is encrypted, this is codified in the Lie group action. And this is a problem, because sometimes you cannot get the Lie group action, okay? But if you can, okay, so you will be able to do this stuff, okay? This used to be useful when you know how to integrate this vector physics alpha, but the time-dependent function is so complicated that you are not able to solve the solution, to find a solution for the Lie system, okay? Okay, so let us continue. The thing is, this theorem tells you that you can obtain the general solution out to a certain particular one, okay? So let us prove this. Imagine that you have a certain particular solution G of t, and imagine that this is the particular solution which satisfies that at the neutral element, it gives you the, well, at the 0, it gives you the neutral element. Okay, so let us work out what is the tangent vector to the solution. So work out the differential of this, and this thing in here can be written as the map at a certain x0, okay? And as before, this thing is the differential of this cube, yeah? But this thing, by definition, it can be written as the tangent map to the right invariant, to the right translation by the element G of t of this element that it is in Lie algebra. Here, the only thing you have to take into account is that this thing in here is just A alpha, is what you wrote before, okay? So now you have to take into account this relation that tells you that if you have an element of, and you multiply by G of t, okay, and you apply then x0 to it, yeah, what you obtain is, this is the same as doing the contraction with G of t, because this is indeed the action on G of t on the point x0, okay? So doing so, it follows the following thing. This part in here, since it's the tangent to r of G of t with the tangent to phi or x of 0, by means of this is the tangent and the neutral element of phi of equals t, okay, with this thing. But you have to remember that this thing in here, when you act on this thing, by definition with the minus, this gives you the fundamental vector field, okay, at this point x of t, because it was done before, yeah? This is an element of the Lie algebra, element of the basis, and when you do the phi on a certain point, and you do the tangent mapping to this at the neutral element of this, you will obtain the value of the fundamental vector field at this point. So this is what is written here. But this linear combination is nothing but the time-dependent vector field at this point, x of t. So that means that x of t defined in this manner is a solution of the Lie system. And this is the solution starting by the point x0. So if you vary x0, you solutions. What we have obtained? that the general solution to the original Lie system can be obtained by means of automorphic one, by means of different particular conditions, initial conditions. So this is why this is so important. Indeed, lately we had application of these, because in numerical methods, Runge, Kuta, and other numerical methods to approximate differential equations, they don't take into account that the orbits of these Lie systems must belong to the must be included in 13 action. When you apply a numerical method to these numerical methods don't care about the fact whether these vector fields respect some foliation or whatever. So they have problems. But if you use these and you apply this and this phi, you will obtain better approximations. So this is from the point of view of numerical methods. Theoretically, it's also important because, well, physicists love solving differential equations, but it can happen, indeed it happened, that they solved different differential equations. They were Lie systems and they were related to the same automorphic Lie system. So what I did while being a PhD, not proving that all the results for different differential equations, they were related to the same automorphic Lie system and they could be solved all together. For instance, something like this, okay? So this is one I think I did while being a PhD. I studied different differential equations. This is, you know, first of all, the system describing an harmonic oscillator, time-dependent harmonic oscillator with a time-dependent frequency. This thing you have in here is, well, it's called a Smorodinsky-Winternitz oscillator. Okay, it comes from a third-time mechanical system. It's also, well, you can relate it also with a problem on the real line with a theta time-dependent potential and one as a typical term. It appears also in quantum mechanics when you try to relate time-dependent quantum oscillator with a time-dependent one, that you need this to solve these oscillators. Here what you have, well, there are many other cases, okay? The thing is that when I found the automorphic Lie systems of these things, they were exact how it was done. No matter if you have this system, an harmonic oscillator, or this equation is sometimes called a mean-pin equation, as Smorodinsky-Winternitz oscillator, okay? You can write these both differential equations as the differential system corresponding to this time-dependent vector field, where x1 is this vector field, x3 is this vector field. This, okay, this is for this one. And you will see that if you have this linear combination and you write the differential equations to this, you obtain this thing. If you make here k equal to 0, okay, this disappears, the relations are exactly the same, and you get this. Okay, so this thing or this thing, there are particular cases for a certain different vector fields with different values of k. They close a Lie algebra. It can be proved that this Lie algebra is homomorphic to SL2, and so they are Lie systems. When you go to the automorphic, you pick up right invariant vector fields closing the opposite relation that this, and by means of this you can express this automorphic system. So this is the way it's done. Well, this finishes the Lie group approach to Lie system. Well, the basic, okay? This essentially was done by Poisson. Well, I did several contributions to this approach, and also I have to tell you that Poisson has several almost impossible to get, and he has a lot of results, and probably didn't get anything, but sometimes it happened that I proved something, I thought that it's new, and it was in one work of the beginning of the 20th century. So this finished one of the approaches. And now we'll go for the second one, that is the foliation approach to Lie system. As I told you at the beginning, this approach was done by Cariñena from the University of Zaragoza in Spain, by Marmo from the University Institute for Nuclear Studies, I think it was in the University Federico III in Naples, and by Grabowski from the Institute of Mathematics of the Polish Academy of Science. Now, the thing is, as I told you at the beginning, Lee had wonderful ideas, wonderful techniques, but his work was written toward the end of the 19th century, so they are not too much precise. Lee by himself, even for the standards of that time, he wasn't the best one explaining himself, and his work led to several misunderstandings. With respect to the Lee theorem, as far as I know, it's only in German. I haven't seen an English version, as far as I remember. And it has several problems, several parts of it that are not properly proved by Lee. That means that they are true. I mean, there is nothing wrong about the theorem, but there is some gaps. And the problem is that for all the researchers recalling Lee's result or writing proof of the Lee theorem, they repeated exactly the same gaps with the same problems. And this was solved by Karinyena, Grabowski, and Mark in 2007. Indeed, this work was done just the first day I started working on this system. Well, first day, the first month. I remember that my supervisor told me, I know a Polish guy, colleague of mine, is doing some stuff that can be interesting. Maybe we are going to add you to this work. Well, finally, it was at the beginning of my PhD, more or less. Now this paper is quite fundamental. It has something like 100 citations or something like that, so it's highly cited. And it's the fundamental of the Follian approach. Winternitz knew about it. Winternitz wrote several papers using parts of this approach, but as Winternitz did, he never cared about the mathematics. He just used what was important to him, and he had very brilliant and nice idea, but there is no single work putting all together in a nice way, solving no problems as Karinyena, Grabowski, and Markov did. So let me tell you what is the main idea of this approach. So for Karinyena, Grabowski, and Marmo, the way of thinking about superposition rule, it was by means of a figuration. Yeah. So, you know, the superposition rule thing is something that you try to have m particular solution, one parameter counting for the initial conditions of your problem, somehow generating a certain solution. So the superposition rule is something that depends on m times n plus 1 copies of the initial manifold, because each one of these m plus 1 entries will be concerned with the first n copies for m particular solution. The last one will be about the parameter generating all the particular solution of the differential equation, and the image will be something on n because you are trying to retrieve the general solution. Okay, so essentially they said, okay, what we are going to do to understand somehow this geometrically. And what we did, it was change a little bit this. We made a manifold with m plus 1 copies of the initial manifold, and another manifold, a basis with m copies of the initial manifold. And we made a projection of this manifold onto the m first copies. I mean, if you have n plus 1 points of n, that is a term in this manifold, you project onto the initial n1s. So essentially what we did, it was that they said, okay, we are thinking about superposition rules as a lift. A superposition rule, when you fix parameter, 1 point of n, okay, in here, it will be something that for m points will give you a new one. So they thought about it, about taking n points and adding the xn plus 1 point, okay, that comes from this. I mean, you pick up this. When you pick up k, a certain parameter, the particular solution with this condition generate a new solution xn plus 1. So instead of writing this thing in here, they write it in here. So you say when you pick up k, a certain parameter in initial condition with the superposition, what you are doing is for every point here, you are lifting it to a point in m plus 1 in such a way that the additional coordinate you are adding, it will give you a solution. So what you are doing is lifting. You pick up this and you put it this way. Okay. So for different values of k, you are foliating this. You have to take into account that when you have an initial point here, you vary k, you are generating a new condition for a new particular solution. So for different values of k, these two manifolds cannot intersect, because if there is no empty intersection, there will be a point where for the same initial conditions, you will get for two initial values the same particular point of the new solution. And this is impossible because for solution of differential equations, if you have 2 points where they coincide, they will be always the same. So this is the way of thinking. They think that the standard superposition rule is a way of lifting, and we can consider a new mapping, a little bit different, which is defined on n+1, but for every n+1 solutions points, which correspond to m solutions undegenerated, they give you the k of the lift superposition rule. And it's satisfied that for n+1 particular solutions, this gives you a constant. So you see, you have a 30 solution of this manifold, and this is what they thought, that a superposition rule is nothing but a lift on a certain boundary. So I will sketch how the Lie theorem works, how it can be proved. So imagine that you have your Lie system, you have your superposition rule, and as for a superposition rule, the general solution can be written this way. A certain function of n particular solution and a certain set of n parameters. These are, for example, the coordinates of a point on the manifold. Yeah. So this is when you fix the initial condition, every particular solution is retrieved by means of certain values of the parameters, and every value of the parameters gives you a certain different particular solution. And this is a relation 1-to-1. When you know, when you have fixed this particular solution, every initial condition is given by a k, and every k gives a particular solution. So you can invert this mapping and to obtain a phi, which is such that for a set of n+1 particular solution, you get the k, which generates x0 out of xm to xm. So essentially, you pick up this and you apply the inverse function theorem to give the value of k1, kn out of the value of x. So out the value of this, you obtain k. And this is the function. Only that you see that this phi thing, it will be a constant on particular solutions. When you pick up certain n+1 particular here, this phi will give you constants. Indeed, remember that if you invert this, for all the points of xt, you put it here like the 0 component, this will go out and you will have always the same constant. So you get that the components of this on n+1 solutions are constant. So if you work out the differential of this, you will obtain the partial function of all of these phi with respect to each of the coordinates and the differential of each one of the coordinates. So you get this thing here. But remember that these are the solution of the original problem. X alpha is the solution number 8, sorry. So this derivative is nothing but the time-dependent vector field of the point x alpha. Yeah. And the thing is, what this is telling you, okay, this expression 5, is that for every value of t, these coordinates psi I are integral of motion of these time-dependent vector fields you have here, this time-dependent vector field. Yeah. But you can see that the t in here is just a parameter. When you vary the t, you have just the psi I is a constant of motion for different vector fields, because a time-dependent vector field is a t-parameter vector field. So to describe this properly, you will define the so-called diagonal prolongation. And diagonal prolongation of the manifold is nothing but a vector field on the manifold n+1, okay, in which the component, the coordinates of this, on the coordinates of each part of the manifold, you have n+1, will be the same functions you had at the beginning, but the x in here will be just the coordinate of one of the copies. So essentially, these you have in here are the same vector field, time-dependent vector field, on each copy of everything put together. So this is what is called a diagonal prolongation. And this is important because the shape of this is exactly the shape of this thing that you have here. And these time-dependent vector fields, they are very important because they are used to prove the Lie theorem. So let me tell you that the expression before can be written that, as I told you, that the psi is a constant for this time-dependent vector field. But for every fixed value of t, this is just a vector field. So this psi, which is a function on n+1 times the original manifold, is a constant of motion of these vector fields. Yeah, these vector fields span a distribution. Okay, and since this vector field span this distribution, okay, and this psi I is a constant of motion of for every x hat t, okay, and this vector field span the distribution, it turns out that the psi they will be constants of motion for all vector fields taking values in this distribution. The thing is, you can prove, by means of a 30 theorem, is quite technical, I will not go through details, that this psi will exist, okay, giving a particular solution, if and only if this time-dependent vector field here will be a linear combination with time-dependent function of 30 diagonal prolongations, okay? And there was a trick to prove that, and the trick was that these vector fields that of the psi I in the diagram I wrote in here, they are constant on it. So these time-dependent vector fields for each value t are vector fields here tangent to these leaves. Okay, so Kariñena, Grambowski, and Marmo prove that these vector fields are such that the projection of them onto this manifold, they must be linearly independent. Okay, if this is the case, this is a technical detail was not in the literature. They could prove quite well the superposition, the Lie theorem. Okay, so let me explain you how this looks in a particular example, because this theorem, okay, tells you how to construct superposition rule by means of distribution. So start by Riccati equation. This is something you can write it in this way as a time-dependent vector field. You remember this is the coefficient of a time-dependent vector field, okay, on the manifold R, because this is a variable belonging to R, and you have this combination. And now these vector fields here 2, 3, they close, as I told you, finite dimensional Lie algebra. This is the Lie theorem. So there is a superposition rule by the Lie theory. How we do it? How we can get it? Okay. If you pick up these vector fields, the Lie theorem tells you that you have to obtain the diagonal prolongation of these vector fields. I mean, pick up this, and you will have to get a prolongation to R2. It will be the same, but this x will be the variable of the first manifold, the second, as the same vector field, but with the variable of the second, the same with this, the same with this. What you will obtain is that you have to check when the diagonal prolongation of these vector fields are linearly independent at every point. Because you see on R, this is partial x, this is x partial x, and this is x squared partial x. So at every point on R, they are proportional, yes? They have the same direction. If you go to R2 and you work out the diagonal prolongation, you will notice that the first and the second, they are generically, at a generic point, linearly independent. But the third is not. Okay, on R2. And if you go to 3, diagonal prolongations, you will get that these free vector fields are linearly independent at a general R free when you pick up the diagonal prolongations. This is the magic of the Lie theorem, and it was proved in my PhD dissertation. It's quite technical, but essentially says that the proof given by Grabowski, Marmo, and Kariñena works, because it was they said that it is true, but there was some missing details. It was not very important, but it was nice to put everything quite properly. So when you do that, what it means is that for free copies of the diagonal prolongation to R free, you can start thinking about working a superposition rule. And that means that exactly that this manifold R free, that is free copies of the original one, okay, it tells you that your superposition rule will depend on three particular solutions. And to obtain the superposition rule, you have to make the prolongation to R4, that is the thing, you say is the partial with respect to a variable, which this variable goes from 0 to 3, because it's the same vector field, but with variables on different manifolds, different copies of the same manifold. And the psi is an integral of these two vectors. It can be proved that on a dimension of on a manifold dimension R4, you have three vector fields. There is just one constant of motion that was found by Lie, and this is 1. And writing x0 in terms of psi, and supposing the psi is a constant, and the remaining ones, you will obtain the constant, the superposition rule. This is the non-superposition rule. So let me repeat. Pick up a third-Taylor system. Pick up a Bessel-Group Lie algebra. Make the diagonal prolongations at the moment you have enough copies of the manifold to be these diagonal prolongation of these vector fields linearly independent generic form. This gives you the number of particular solutions. Extend to the following manifold. Work out the integrals of motion. Essentially, this integral of motion, some of them, will allow you to write the additional coordinates of the manifold in terms of the others. And this will be the superposition rule. This is the method. Okay. Let me tell you how we obtain the solution of these partial system differential equations. Well, you will have to pray to God or to someone, or because sometimes it's almost impossible. Sometimes it's difficult, but it is possible. And let us say that it's tricky in general, but it is easier than solving the initial. In general, it's easier than solving the Riccati equation. There are, in general, no analytic solutions of this differential equation for general time-dependent functions. Okay, no general method, let's say this way. And but the superposition rule exists, no matter what is A1, A2, A3. Sorry, there's a mistake in here. So this is able, you can use it even when you cannot solve this. And when I did this, I noticed that there's typical solutions solving this partial system differential equation was very, very difficult. And my first PhD student, and we proved that these solutions for certain kind of system called Hamiltonian systems can be obtained trivially. I mean, it's a matter of, it takes 5 minutes, okay? So my first PhD, Cristina Sardón and I, proved that the usual way of solving this differential equation was too complicated, and it should be done by means of symplectic geometry. And this will be the topic of the following talk, that will be about geometric structures and these systems. I will review symplectic manifolds, and I will give some other structures, and I will tell you how this allows us to obtain superposition rule, properties, and many other things about the systems in a more beautiful way, and how it allows one to use advanced differential geometry to study dynamical system in a very elegant way. So this is the end for today. Thank you very much. This is everything I wanted to tell you. I hope that it was somehow interesting. Thank you.
Thank you, Javi, for this talk. Are there any questions or comments? No? No one?
My superposition rules. Okay, so we can finish maybe
Yes.
next about differential geometry, and it was more geometrical. It was a little bit change of topic.
Okay, so thank you all for attending and see you next week.